What you are seeing is not movie special effects. This is reality unfolding at a height of 359 meters above the Chenab River level, located deep within the Himalaya mountains. To give you an idea of this scale, if we picked up the Eiffel Tower of France and placed it into the riverbed below, the top of the tower would still be 35 meters lower than this bridge deck. This is the Chenab Bridge, the highest railway bridge on the planet. But the number 359 meters, or the $5 billion budget, is not the craziest part of this project. What truly makes engineers around the world hold their breath lies in its location, the Jammu and Kashmir region. This is one of the harshest places on Earth to build, gathering the deadly trio: high-magnitude earthquakes, destructive wind speeds, and complete isolation from the civilized world. How could humans transport 30,000 tons of steel through vertical cliffs with no roads? Why, in a place with wind speeds up to 266 kilometers per hour, did engineers choose a steel arch structure instead of the usual cable-stayed or suspension bridge? And the biggest question, how do you hang massive steel blocks weighing tens of tons in midair and assemble them with millimeter precision when below is a deep abyss with absolutely no support points? In this video, we will explore together how Indian engineers built the highest bridge on the planet. Before we start, don't forget to hit like and share this video with more people. Now, let's get started right away. To start this project, the engineers had to solve the first problem: access. The construction area was so remote that previously no roads existed. Therefore, the mandatory strategic move was building a 26-kilometer access road cutting through the Rocky Mountains. The road opening process was carried out using a risky, step-by-step method. First, worker teams had to use specialized ropes, hanging themselves directly on the vertical cliffs. They used handheld drills to create holes for explosives deep into the mountainside. Then, controlled blasting techniques were activated to peel off hard granite layers precisely without shaking the entire mountainside. As soon as the dust settled, small crawler excavators immediately entered the danger zone. Here, the operator had to both push tons of rock into the abyss to create a level surface and be cautious every inch with the unstable ground beneath. Specifically, as they progressed, they had to install steel mesh and spray concrete to reinforce the cliff face. This ensured falling rocks wouldn't hit the construction team behind. Just like that, every meter of road was wrestled from nature's grip. It took years of relentless work for this lifeline road to be officially opened. After the road was gradually completed, let's go back to the manufacturing plants in the plains to talk about materials. The total amount of steel needed for this project amounts to 30,000 tons. This figure is 4 times the weight of the Eiffel Tower. However, bringing this massive amount of steel from the factory to the mountain peak was a terrible challenge. Look at the hairpin turns on the single road we just opened. The turning radius is extremely narrow, with a cliff on one side and an abyss hundreds of meters deep on the other. This meant that using heavy haulers to transport monolithic bridge beams tens of meters long up here was impossible because the trucks simply couldn't make the turns. Therefore, the engineers were forced to choose the solution: on-site fabrication. Steel was cut into compact module plates right at the factory to fit the truck bed size, then transported up the mountain. Upon arrival, a massive field workshop was erected right on the edge of the cliff. Here, welders would start joining each small piece back into complete structural components for assembly. When tens of thousands of tons of materials were fully gathered at the edge of the abyss, the vital technical question truly began: what type of bridge will we build? The engineers had to face the biggest enemy in this valley: wind. Survey data showed that wind gusts here could reach 266 kilometers per hour, equivalent to a major hurricane. Initially, many suggested cable-stayed or suspension bridge options, because they are common and easier to construct. However, in bridge engineering, these two types have a fatal flaw. Their structure is very soft and flexible. At a height of 359 meters, under the continuous impact of high winds, a cable-stayed bridge is prone to resonance oscillation. The bridge could twist and shake violently. This is forbidden for railways, where trains need an absolutely stable and rigid plane to travel safely. Therefore, after many calculations, the optimal and only solution selected was the steel arch structure. Unlike suspension bridges which withstand tension, arch bridges operate on the principle of compression. The bow shape gives it extreme structural stiffness. It remains rigid and solid, not deforming under wind pressure. The entire weight of the train and the bridge will be converted into compressive force, transmitted along the two arch ribs, and pressed tightly into two massive foundation blocks at both ends. To realize this design, the first construction stage undertaken was foundation work. Engineers had to dig deep into the rock face, pouring thousands of tons of reinforced concrete to create two eternal pedestals. They anchored the bridge feet tightly into the mountainside, turning the Himalayan cliffs into part of the load-bearing system. The harder the cliff, the more stable the bridge. The foundation was done. Now it was time to assemble the backbone of the structure, the massive steel arch. But with the distance between the two cliffs reaching nearly 500 meters, no crane could reach. To solve this, engineers had to create a giant tool themselves, a cable crane system spanning across the sky. First, they erected two towering steel pylons on the opposite peaks. The next challenge was how to get a steel cable weighing tens of tons across the valley. Engineers had to deploy a specialized helicopter, flying from one bank to the other to drop a pilot wire. This tiny pilot wire acted as a guide. It was connected to a powerful hydraulic winch system to pull a larger cable, and finally to pull the large diameter main cable into position atop the towers. When the cable system was tensioned, the sky above the site officially turned into a mobile assembly plant. Now the trolleys on the cable started working. They picked up each steel arch segment from the yard, moving it into midair for welders to assemble. The erection process was carried out simultaneously from both banks, reaching out to the middle of the river. To keep these heavy steel segments suspended in the sky without falling into the abyss, after installing each segment, engineers used a temporary stake cable system to pull them back towards the cliff. These cables acted as arms holding tight to the two arch halves. Parallel to the assembly, a special reinforcement technique was executed immediately. After the hollow steel tubes were positioned, high-pressure fresh concrete was pumped to fill the inside. This combination created a super strong structure. The steel shell withstands tension, the concrete core withstands compression, helping the bridge withstand strong seismic tremors. The most dramatic moment of the project arrived when the two arch halves met in the middle of the valley. At this point, the temporary stake cables were slowly loosened to let the two arch ends lower and interlock. The allowable error was measured in millimeters. When the final locking pin was closed, the arch officially became a unified block, standing firm in the blue sky without needing any supporting cables anymore. When the bridge arch closed and stood firm in the sky, it became a perfect support base for the next stage, constructing the deck where trains would directly roll. But how to place tracks on top of that towering curved arch? Instead of dangerous construction midair, engineers used the incremental launching method. They turned the hard ground at the bridgehead into a fixed factory. The process went like a continuous production line. First, they cast and finished a beam segment right on the ground. Then a massive hydraulic jack system would push this segment to slide out towards the abyss. Immediately, the empty space behind would be used to cast the second segment. The second segment was rigidly connected to the tail of the first, and both were pushed forward together. Just like that, the road lengthened meter by meter. However, there was a serious physical problem. When the concrete block weighing thousands of tons slid into the void, gravity would pull the bridgehead down into the abyss before it could reach the next support pillar on the arch. To solve this, engineers attached a lightweight steel device to the front called a launching nose. This nose is much lighter than the bridge beam. It acts like an arm reaching forward, bridging to the next pillar. When the launching nose touches the pillar, it shoulders the gravity, creating a solid track for the heavy concrete beam behind to slide safely across to the other side. And the final piece for this structure to survive for 120 years is solving the problem: temperature. In this mountain region, the temperature changes drastically from 0 degrees Celsius to 50 degrees Celsius. According to physics, steel expands when hot and contracts when cold. If we rigidly fix the bridge to the cliff, this expansion force would accumulate and tear apart welds or buckle the train tracks. To neutralize this, engineers installed a spherical bearing system at the contact points between the deck and pillars. This device works exactly like cartilage joints in the human body. It allows the deck to slide freely and rotate slightly on the pillars when the temperature changes. Thanks to these flexible joints, the bridge can breathe rhythmically with the weather, completely eliminating thermal stress that could destroy the structure. So, we have walked through the entire journey of building a masterpiece. From the first rock-blasting drills carving the path on vertical cliffs, to the wise decision of choosing the arch structure to defeat the windstorms, and finally the absolutely precise launching technique. The Chenab Bridge is the most eloquent proof that, when humans combine courage with logical engineering thinking, no natural limit is impossible to overcome. $5 billion and millions of labor hours were poured into this valley. The result is not just a railway connecting the isolated Kashmir region to the rest of India, but an eternal symbol of the power of human intellect. In this entire risky construction process, which stage impressed you the most? The danger of road building or the precision of the arch closure? Leave your analysis in the comments section below. Don't forget to like the video and subscribe to the channel to fuel us to make the next mega project videos. Goodbye and see you again.